Okay, this video is going to introduce differential equations. And what differential equations are, we've been dealing with them a bunch this year. I just haven't used the word differential equation. A differential equation is any equation that has a derivative in it. So y prime equals 2x is a differential equation. Y double prime equals x squared is a differential equation. Dy dx equals yx is a differential equation. It's an equation that has the derivative in it. That's it. So what we're going to do right now is to look at solving some different types of differential equations. Obviously, the ones on over here on the left side are ones that you guys have solved a bunch this year. Whereas the one on the right side here is new and different, and we need a new technique for being able to solve differential equations that look like that. Okay, let's first look at this differential equation. Dy dx equals 2x. And you guys have solved ones like this a bunch this year, but what I'm going to do is something a little different this time. I'm going to do something called the separation of variables. I'm going to get things with y on the left side and things with x on the right side. So by multiplying both sides by dx, I can write dy is equal to 2x dx. And then if I anti-differentiate both sides, on the left side I get y plus some c, I'll call it c1, is equal to x squared plus some constant, we'll call it c2. Now, what I can do, though, is I can take these two constants and I can combine them. I can move this c1 on the left side over to the other side. So what happens is this goes away, and I guess I could call on the right side, I could call it c3, but I'll just call it c. That c will be some constant. That's the mixture of those two constants. And there we have. The solution to that differential equation is y equals x squared plus c. Shouldn't be surprising. But this same sort of technique allows us to solve other types of differentials. All right, so here's one that we looked at already this year. Dy dx equals y. This is a differential equation that we talked about earlier this year, and we thought about what are the solutions, possible solutions to this equation. Where is the derivative equal itself? And one obvious solution is y equals e to the x. And if you think about it, another solution would be, I don't know, y equals 3e to the x. And y equals 0 also works. Each of these functions, its derivative is what it was originally. So dy dx is equal to y. In fact, if with a little more thought, you can say, okay, well, it doesn't matter. The constant in front could be anything, c e to the x. So the question is how do I go from this equation, this differential equation, to this equation? And the separation of variables is the key. Okay, let's start with dy dx equals y. If I separate, I get dy over y equals dx. And if I anti-differentiate, the left side becomes the natural log of the absolute value of y, and the right side becomes x plus c. And that c, again, is the combined constant from the left and right side, just moved over to the right side. And if I solve this for y, I get the absolute value of y equals e to the quantity x plus c. Now, this is why it's important to think about, not to forget about your plus c. I've been bothering you guys all year to think about the plus c, and the reason is now is because if you notice, this plus c is no longer something I can tack on at the very end of the problem, because now it's up in an exponent. It's in a different spot, and it's not going to be just the very end of the problem plus c. Doesn't work right now. And if I keep going with this, I can simplify this a little bit. I can say that this means absolute value of y equals e to the x times e to the c. And if I think about it, well, e to the c is just some constant, so I can say that the absolute value of y equals some constant times e to the x, and that constant would have to be positive because e to the c is positive. And it's okay to use the same variable, c here and c here. I mean, in theory, you should probably number C1, C2, but even the College Board's okay with it to kind of be informal in moving this stuff around. But what we can think about is this C here is positive, and both, if I write this, the absolute value of y equals c to the x, which means y equals either positive or negative c e to the x. And then it's like, okay, well, the plus or minus, I can have that get absorbed into the c, and so I get y equals c e to the x, where that c could be positive or negative. And there's the solution. So I started with this differential equation, and I ended up there with y equals c to the x. So that confirms what we thought earlier. Okay, let's look at another differential equation. Dy dx is equal to, let's see, make it negative x over y. And before we start solving this equation, it's useful to think about what properties the solution is going to have. And the differential equation will tell you lots of things. One is, well, when x is 0, the slope of the solution, whatever the solution is, the slope is 0. When x is 0, the slope is going to be 0. Likewise, if y is 0, the slope would be undefined. Other things to look at is if x and y are the same, then the slope would have to be negative 1. And if x and y are opposites, well, then the negatives will cancel and the slope will be positive 1. So it helps to maybe think about any graph that you can think of right now before we solve this differential equation where it has those properties. The slope is 0 when x equals 0. The slope is undefined when y equals 0. The slope is equal to negative 1 when x and y are the same, and the slope is equal to positive 1 when x and y are opposites. And you might be able to envision what that graph might look like. And, well, we'll separate the variables, we'll solve this differential, and we'll get an idea exactly what it must look like. So separating the variables, I get y dy equals negative x dx. And if I anti-differentiate both sides, I get 1/2, I get 1/2 y squared is equal to negative 1/2 x squared plus c. All right, now what I'm going to do, this equation might be looking familiar at this point, but what I can do to make it look more familiar is I can multiply both sides by 2, clear those fractions, and I'll get y squared equals negative x squared plus 2c. But what's 2c? Well, 2c is a constant, so I'll just write that plus c. And if I move that x squared over, I get x squared plus y squared is equal to c, which is an equation you should recognize because that's a circle with radius, well, radius root c. But what's true about a circle? If you think about a circle centered at the origin, the slope is 0 when x equals 0. The slope is undefined when y equals 0. The slope is negative 1 when x and y are the same, and the slope is positive 1 when x and y are opposite. So it's definitely the solution to this differential equation. Totally makes sense. And this is the general solution. If we knew a point that was on this graph, I could plug in the x and y and find what c would be. But right now, this is the general solution to this differential equation. Okay, so one thing I can do here is I'll take this equation here. I'm going to solve for y. So I'll just square root both sides and get y equals the square root of negative x squared plus c. And I guess a plus minus in front of that. It doesn't really matter which one I do. I'll do the plus. So if I take the derivative of this, I get y prime equals 1 over 2 square root of negative x squared plus c, and then times by the chain rule negative 2x. And if I simplify this, the 2's cancel out, and I'm going to have negative x over the square root of negative x squared plus c. And if you look at it, what I have here is, up top I've got negative x, and the bottom I've got y. the same y that was here. And if I had chosen this to be negative, there would have been a negative down here, and well, I guess you could say the negatives cancel, but it would still be the quantity negative x over y, so it still works. All right, well, the separation of variables does have its limitation. For example, if I had this simple-looking differential equation, dy dx equals x plus y, and I try to separate the variables. I try to get this stuff with x's on one side, stuff with the y's on the other. I'm going to have a tough time. In fact, I can't do it. So this one is an unseparable equation. I can't get the y's together and the x's together. I always have to have a mix of them. So it's going to fall short. We're going to have to learn some other techniques for dealing with this differential equation. We do know a few things, though, by just analyzing this. I know that if whatever the graph of this, whatever the solution of this looks like, I can tell you that the slope will be 0 if x and y are opposites. So anywhere, if the graph intersects the line y equals negative x, any point on the graph along that line, the slope would have to be the slope would be 0 because x would equal negative y, and these would cancel each other out. So the slope would be 0 there. I also know that if the point 2, 4 was on the graph, the slope would be 6. So these types of things I do know from this differential equation, but I'm at a loss right now of how to actually solve this one. So the homework won't have any ones like this, but this is unseparable. So hopefully that will help you with the next assignment, and I will see you guys in school on Thursday. All right, thanks.